Question 9. Part A. Explain why the sum to infinity of a geometric series with common ratio r only converges when the modulus of r is less than 1. We know from the formula booklet that the sum to n terms of a GP is given by a times 1 minus r to the n, all divided by 1 minus r. So if n is infinity, this sum is a 1 minus r to the infinity over 1 minus r. So it's dependent on r to the power infinity. If r is a fraction which is less than 1, let's just take a positive fraction to start with. When you take that fraction to a power, the fraction gets smaller and smaller. If you took 9/10 and squared it, you get 81 hundredths, 0.81. It's getting smaller and smaller, so this series would converge. This would also happen if r was a negative fraction which was greater than minus 1. So if r has a modulus less than 1, this series will converge to a over 1 minus r. If r was greater than 1, r to infinity will diverge. It will get bigger and bigger. Anything bigger than 1, when it's taken to a power, will get bigger and bigger. So this would diverge. So this series only converges when the modulus of r is less than 1 and its sum to infinity is a over 1 minus r, which is given in the formula booklet. Part B. A geometric progression V has first term 2 and common ratio r. Another progression W is formed by squaring each term in V. Show that W is also a geometric progression. Given that the sum to infinity of W is 3 times the sum to infinity of V, find the value of R. So let's look at the first thing we have to do is show that W is also a geometric progression. Let's think about the series V. It has first term 2, common ratio R. So first term is 2, common ratio is R, so the next term is 2R. The next term is 2r squared, 2r cubed. This is the first term, this is the second and third. The sixth term is 2r to the 5, so the power is 1 less. The nth term is 2r to the power n minus 1. So we know about series V. W is formed by squaring each term in V. So W is 4r squared, 4r to the 4th, 4r to the 6th, 4r to the 8th, 4r to the 10th, and this term would be 4r, and if we square it, the power will be 2 bracket n minus 1. We want to show that W is a geometric progression. If we look at W, it is 4r squared, 4r to the 4th, 4r to the 6th. Every time we times by r squared, so the common ratio is r squared. If we wanted to look at this more mathematically, we could say that n plus 1th term would be the next term here, so n would become n plus 1, and n plus 1 minus 1 is just n, so we'd have that n plus 1th term is 4r to the 2n divided by the nth term, which is 4r squared to the n minus 1. The 4's will cancel, so we'll have r to the 2n divided by r to the 2n minus 1, so we subtract the powers, which is 2n minus 1, 2n minus 2n goes, and we get minus 2, so the common ratio is r squared. So we have proved that this is a geometric progression with common ratio r squared. The sum to infinity of w is 3 times the sum to infinity of v. So let's think about that. The sum to infinity of v has a first term 2 and a common ratio r. The sum to infinity is a over 1 minus r, so it's 2 over 1 minus r. The sum to infinity of w is got to be a over 1 minus r. A is 4 and r is r squared, so it's 4 over 1 minus r squared. So we know about the sums. Let's just relate it to the fact that the sum to infinity of w is 3 times the sum to infinity of v. So the sum to infinity of w, 4 over 1 minus r squared, is 3 times the sum to infinity of v. So we've got this equation. So if we rearrange that, 3 times 2 is 6, so if we divide by 6 we'll have 4 over 6, which is 2/3, 1 minus r squared over 1 minus r. But we should know that this is the difference of two squares. 1 minus r squared is 1 plus r times 1 minus r. When we times it out we get 1 plus r minus r, so they cancel, minus r squared. So we know that's the correct factorisation. And 1 minus r is going to cancel, so we're going to get 2/3 is 1 plus r. So we could times by 3 and we get 3. 1 plus r is 2. So 3 plus 3r is equal to 2. And if we finish that off, then r is equal to minus 1/3. Or we may have said, when we'd cancelled the 1 minus r, 2/3 is equal to 1 plus r, so the r is the 2/3 minus 1, which is the minus 1/3. Notice if we didn't spot the difference of two squares, as our method made this equation much easier to solve, we would have cross-multiplied here and got 2 times 1 minus r is 3 times 1 minus r squared. So 2 1 minus r is 3 1 minus r squared, so we get 2 minus 2r is 3 minus 3r squared. Rearranged gives 3r squared minus 2r minus 1 is equal to 0. Factorised gives 3r plus 1 times r minus 1. If we check, we get 3r squared plus r minus 3r, which is minus 2r, minus the 1 is 0, so r is minus 1/3, or r is 1. r is minus 1/3 is the solution we want. If r is 1, all the terms would be the same and we really wouldn't have a GP. So it's always useful if we remember that 1 minus r squared factorises to 1 plus r times 1 minus r, because sometimes it means we can cancel and get a much simpler equation to solve. So look out for anything that can cancel when it is the difference of two squares. Part C. At the beginning of each year, a man invests £5,000 in a saving account, earning compound interest at the rate of 3% per annum. The interest is added at the end of each year. Find the total amount of his savings at the end of the 20th year correct to the nearest pound. We must read this carefully. It says at the beginning of each year a man invests £5,000 in a saving account. So in the first year he'll put in 5,000, in the second year he'll put in 5,000, third year he'll put in 5,000, and then we have to deal with the interest as well. So the first £5,000 that he invests earns interest for 20 years, and so it is worth 5,000 times 1.03 to the power 20. The next 5,000 he invests at the beginning of the second year earns interest for 19 years and is worth, after the 19 years, 5,000 times 1.03 to the 19. And this is going to go back and back until the amount invested in the last year would be worth 5,000 times 1.03. So the geometric series is developed this way. So if we look at this geometric series, so if we take out 5,000 as a common factor, we're left with 1.3 plus 1.03 squared plus 1.03 cubed and so on up to 1.03 to the power 20. So we've got this geometric progression with A is 1.03, R is 1.03. So this can be subbed into the formula. So let's take the 5,000 out. We know the sum to n terms is a 1 minus r to the n over 1 minus r. A is 1.03, r is 1.03, so let's sub in. And if we evaluate this expression, we'll get 138,382 pounds to the nearest pound.
This is really quite a difficult geometric progression question. You have to read the question very carefully, as has been mentioned in the solution, and you've got to take care to be quite precise with your notation and everything. The only thing I want to add to it, because these are revision videos, is the proof of the formula for the sum of the series. And there's a good thing to connect it to, which will jog your memory if you can't quite remember the proof under the pressure of an exam. And that's to remember back to recurring decimals. So if we look at, say, 0.3 recurring, and we want to turn that into a fraction, then what we say is that x is 0.3 recurring and 10x is 3.333. So the 3 recurs again. Then we subtract. 9x is equal to 3. And what happens is that all of these 3's cancel each other out. So we are just left with the 3. And then, as you will probably remember, x then becomes 3 over 9, and x is a third, which we know anyway. But the point is that we do this by shunting the digits along. And this is essentially the same technique as what we use for the sum of a geometric series. So the sum of the first n terms is going to be the first term, plus the second term, plus the third term, plus all the way to the final term, which is r to the n minus 1, because we didn't have an r with the first term. So we can see that the second term just has r, the third has r squared, and so on. And now this is the clever trick, which is the equivalent of this 10x trick for recurring decimals. We times by r, and a becomes ar, ar becomes ar squared, so on. Ar to the n minus 2 becomes ar to the n minus 1, and ar to the n minus 1 becomes ar to the n. And then when we subtract, on the left hand side we have 1 Sn, take away r Sn, and on the right hand side we have a plus naught plus naught plus dot 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 plus naught, and then minus ar to the n, because we're subtracting that from nothing. This then tidies up to a times 1 minus r to the n, and then we get our final form, a 1 minus r to the n over 1 minus r. Now, it's worth mentioning that that also is the same as saying a times r to the n minus 1 over r minus 1, because we've just times the top and the bottom by minus 1. If you were then asked to prove that S infinity, or the sum to infinity, is a over 1 minus r, you would say if mod r is less than 1, this implies that as n tends to infinity, r to the n tends to 0, therefore the sum to infinity is a times 1 minus 0 over 1 minus r, which is just a over 1 minus r. And there we are.